Okay. So I will echo.
Hello.
Okay, so good afternoon. So first of all, I would like to welcome all of you to this GATI Symposium today. So to begin the proceedings, I first invite Professor Vidyadhi Raja, Dean of Fellowships and Extensions, to welcome all of you. Raja?
Thank you, Kavita. It's my pleasure to welcome all the speakers and the other participants of this program. So let me begin by saying that all of us who are present here and elsewhere will certainly acknowledge that there is a very strong gender imbalance at all levels in academic institutions, starting from students to faculty members, and the gender imbalance basically grows as we go up in the hierarchy. And the underlying reasons for such gender imbalance could be many. And I'm not an expert on these, but I can certainly point out, but let me not go into the details. But one of them that I believe is very important and leads to a reinforcement of the gender imbalance is as follows. So one of them could be that the admission, enrollment, hiring, promotion, and incentives frameworks that exist today do not incorporate or implement gender equity. And an existing gender imbalance, which is presently existing in our culture, in our academic institutions, would suggest that the existing policy makers who make these policies for enrollment, hiring, etc., would have inherent biases and prejudices, and this will definitely reinforce the existing gender imbalance in the future as well. And what we need to recognize is that this is a kind of a vicious circle, and this vicious circle can be broken only by certain active measures. And one such active measure is this Gender Advancement for Transforming Institutions, that is GATI, which is a pilot program launched by DST in the year 2020 on the National Science Day in Vigyan Bhavan, New Delhi. And the GATI model is basically, the GATI program is basically a program that aims to guide institutions on bringing back the gender balance and gender equity. And how does it plan to do that? So one of the things that GATI has is there is a GATI charter, okay, that has 10 key principles that first of all acknowledge that there is a gender imbalance. Yes, sir. Yeah. So one of the things that GATI aims to do is for institutions to follow a certain charter, and that charter has 10 key principles, which first of all acknowledge that there is an existing gender imbalance, and also give certain guidelines and promotes institutions to come up with frameworks that will bring back or not bring back, but will bring in gender equity. And finally, this GATI program also mandates institutions to undergo a self-assessment program under which the institutions would fill out a questionnaire with certain numbers, statistics, and qualitative inputs. And these will then be assessed, and then based on that, a certain accreditation and a GATI award will also be given to certain institutions. And in fact, JNC is a proud partner in this initiative, and as our President Professor Kulkarni has also said, we will definitely adopt transformative measures to establish equal opportunities across all sections of employees in STEM areas. So, just to introduce the program today, so today we are here to attend a symposium on black holes and fireflies that is organized by the GATI team here at JNCASR. And there will be two talks, one by eminent astrophysicist, Professor Prajval Shastri, who is presently an emeritus scientist at RRI. And she'll be talking about the heftiest things ever, black holes as we know them. And the second talk will be by Professor Ramakrishna Ramaswamy, who is a visiting professor at IITD and has spent a large part of his career at JNU, New Delhi. And he'll be talking about generalizing the notion of synchronization. And these two talks will be followed by a panel discussion on gender imbalance in science. And I will close now by saying that there will be, I hope that all of you will enjoy the talks, all of you will participate in the discussions, and you will come up with novel ideas and implementation strategies to help the GATI team at JNCASR evolve a sustainable framework for promoting gender equity. Thank you very much.
So thank you, Raja, for defining the problem, and I hope we can find a solution at some point. Okay, so we'll start the scientific part of the symposium. And our first speaker is Professor Prajval Shastri. So Prajval is an astrophysicist of nearly 4 decades. She's interested in understanding the physics of giant black holes. She received her PhD from TIFO Mumbai and did postdoctoral work at UT Austin, UC Berkeley, and Harvard Smithsonian Center for Astrophysics. And she was, until recently, a faculty at IIA Bangalore. She's currently Emeritus Scientist at RRI and also Adjunct Professor at the International Center for Radio Astronomy Research in Australia. Prajval is extremely passionate about science outreach. She's also deeply concerned about inequities in science. She's founder and past chair of the Gender and Physics Working Group of the Indian Physics Association, and she's also vice chair of the Women in Physics Working Group of the IUPAP. So today she will tell us, to begin with, about, she'll introduce us to giant black holes. Prajval.
Okay. Thank you very much, and it's a pleasure and privilege to be here and talk about these things. And as is clear, the first part has nothing to do, perhaps, with gender inequity. So I'll start with what are black holes. So we all know that black holes, perhaps we all know that black holes are chunks of space-time from which even light cannot escape. And one fictitious example is Gargantua from the film Interstellar, which you perhaps know had a very realistic simulation of a black hole. Not just of a black hole, but a black hole that is munching. Meaning if material comes very close to the black hole, as you can imagine, the black hole will pull that material towards it. But in the process, because any material in the cosmos most likely tends to have some spin, that material will sort of swirl around the black hole and then plunge into the black hole. And in the process of swirling around, it will be accelerated and therefore heated and therefore shine. And so such black holes can be spotted by us. Otherwise, black holes are black and we can't see them, right? So Gargantua in Interstellar was an example of that kind of a black hole. And if they are munching, we can spot them. So black holes are sort of projected as a very modern thing, but actually they're a very, very old idea, as old as in the 18th century, documented, and we can think about them even from high school physics and the notion of escape velocity. So we know that if we throw something on Earth, it will fall to the ground. If we throw it faster, it will fall further away, and there comes a speed, if we keep on increasing the speed, when it will escape from the Earth. And there's a formula that goes along with that we learned that in school. And the crucial thing is this distance from where we are doing the throwing. And so if we keep the same mass, say the mass of the Earth, and squeeze it to a smaller size, then that value goes down. And so then what happens to the escape velocity? It increases. So you imagine a situation where you squeeze it so hard that the escape velocity becomes the velocity of light. It turns out that if you do that, play that game, the formula that comes out is correct and it's consistent with general relativity. And it turns out also that if you have to squeeze it to like a marble, which is very unrealistic. So this was also realized in the 18th century. And so any realistic black holes, and indeed the smallest black holes we know, are cosmic. So we know since then that heavy stars collapse into black holes at the quote-unquote end of their lives. And you have such black holes strewn all over our Milky Way and also all across other galaxies. And LIGO, the Gravitational Wave Observatory, has discovered many, many black holes coalescing. So these are mostly these kinds of black holes, which are due to the ends of stars' stellar lives. And one of the biggest, for example, had a mass which is 175 times the mass of our sun, which was the result of a coalescence of 107 solar mass and a 77 solar mass black hole. So these are, as I said, strewn all across the galaxy, and also external galaxies. However, even as early as in the 60s, there was evidence for black holes, but much, much bigger ones. For example, there was this galaxy, a very innocuous-looking collection of swarming stars. But if this galaxy were imaged at radio frequencies, it would show these outpourings of plasma. And we know that because we know this is synchrotron emission by measuring its spectrum, etc. So the pink stuff is a false color picture of a radio frequency photograph. And you can see that the plasma has gone right out into intergalactic space. So this is the galaxy itself, billions of stars. And from the center, spew out these synchrotron emitting jets all across into intergalactic space. And the only way to make these or to understand these was to posit that there was a huge black hole, meaning more than 1 million solar masses of mass at the center of this galaxy. So this kind of black hole is different from the ones I just mentioned before, which are the end of stars. And so the idea is that there is such a giant black hole in the center. If matter comes near it, as I said earlier, it will swirl around and plunge into the black hole. But black holes are messy eaters. So because this matter gets so hot, it is plasma, it's ionized, it generates magnetic fields, and these magnetic fields are long ordered magnetic fields on large scales. So they produce jets of plasma, which are then spewed out into intergalactic space. So all the material doesn't plunge into the black hole. Some of it is spewed out in the form of these jets. And that is what is sort of shown here. This is just a sketch, but this is real. These data are real. So this was the evidence for giant black holes in the center, supported by computer simulations, where plasma is proximity of a giant black hole, and you apply relativistic magnetohydrodynamics, and that is how this simulation was produced. And the green lines are around such a strong gravitational field, it will generate these synchrotron jets. But again, it's still circumstantial. This is one example from my own work. This is a galaxy. This is a galaxy called the Carafe because of its distorted sort of carafe shape, which is one of a trio of galaxies. They're gravitationally interacting. And we imaged this at multiple wavelengths. So at in visible light, using what is called an integral field unit, which is just a boring name for a two-dimensional spectrograph, which means that we take a spectrum of each piece of this galaxy. And we also observed it at radio frequencies and at X-ray frequencies. And So what this is showing is, this is the same image. This is the same galaxy imaged at infrared frequencies, which shows those two, which actually tells us that this is not one galaxy, but two galaxies having merged. And therefore, as predicted, we would predict their central black holes to also merge. So that is this and this. This third thing is just a foreground star. We see the same thing in, this is that spectral image that I talked about. So we've superposed images at different frequencies which are emitted by certain atomic excited states. So this has doubly excited oxygen and also H alpha and N2. These images taken in oxygen 3, H alpha and N2 put on top of each other in different colors. And again, you can see the effect of the two giant black holes which are accreting. And this is a radio picture of the same thing. So it shows synchrotron emission at the same positions and also shows X-ray emission with the Chandra X-ray telescope. So if you think about it, if some giant black holes are munching, there must be others which are not munching, which we wouldn't see because they are just sitting there quietly. And indeed, we know now that every galaxy has at its center a giant black hole. And therefore, then there must be one at the center of our own Milky Way. And that was the result which got the Nobel Prize in 2020, wherein it was a result of work over starting 1995, where they peered into the center of our galaxy using infrared frequencies, because you can't peer at using visible frequencies because of all the gas and dust in the line of sight. And they actually imaged the stars in that very central region with this telescope. And what you see here, these multicolored splotches, each of them is a real star. And you saw in the, this is not a simulation, these are real data, just an animation of images taken at different times, the time given in the corner up there. And then all these images put together to make an animation so that you can see how these stars are actually moving. And you notice that they all moved in elliptical orbits. Not only that, all the elliptical orbits had the same focus, which is marked by this star-shaped thing. Just to be confusing, it's not a real star, it's just marking that position. And so what does that tell us? It's very reminiscent of our own solar system. The orbits are Keplerian. We can deduce the mass of this thing that we can't see, actually. There's nothing there that we can see in infrared or even visible light or anything. And so there must be a mass which is driving these stars in elliptical orbits, and that mass has to be smaller than the closest approach of this particular star, because the star approached close and then again continued along that elliptical orbit. It didn't get deflected in some other direction, which means that whatever is driving it gravitationally has to be really, really small. So that the result of this study was 4 million solar masses of a dark mass. It has to be a black hole because it's so small. That is at the center of our own Milky Way. Now, this is dynamical evidence, which is better than the circumstantial evidence I mentioned before. But what is the real evidence for a black hole? Now, we know that as per general relativity, mass tells space-time how to curve, and therefore masses must bend light. Any mass, your mass, my laptop mass, but it has to be big enough to be perceptible. And this was demonstrated over a century ago by the famous experiment of Eddington at the eclipse. And so if you imagine this piece of sky, which contains our Milky Way, if there is a black hole somewhere, it should bend the light from all around it. And we should see a silhouette like this, right? That is our ideal. However, the kind of contrast you can imagine, because this is just background light from the sky. So the kind of contrast between this and this is extremely low, apart from the fact that you need a very, very sharp picture in order to see these silhouettes just the way things are. Because even with these giant black holes, which are really big in size as well, we still don't have telescopes that are sharp enough to image this kind of size. However, there is one saving grace. So these galaxies, which I showed you before, which have munching black holes. So I said that the matter around them is swirling, heated, and therefore shines. So when you have shining matter, that will create a high contrast between the silhouette of the black hole and the light from around the black hole. So that was used for this particular galaxy with something called the Event Horizon Telescope, whose details I will skip, but there are very, very nice pieces on it and videos and so on the net. So this galaxy is called MESI 87. It's somewhere near the Spica object. This is a zoom in on Google Sky. This is what the galaxy looks like, just a swarming collection of stars. And at radio frequencies, it turns out it's not only spewing out plasma, which goes into intergalactic space, but it has been doing that for a very, very long time, as a result of which this plasma is extended to, a huge extent. So these structures are extremely large. And what the Event Horizon Telescope did was to take the sharpest image ever by zooming in to the center. And there you go, the silhouette of a giant black hole. So this is really, really direct evidence, as direct as you can get for the existence of a black hole. So this is that whole galaxy, and it's resulting, the new image with this Event Horizon Telescope it's like zooming in 1,000,000 times in the center to give this structure. And more recently, they did the same thing at the center of our own Milky Way, and again found the same kind of structure, the silhouette of a giant black hole, as we would expect. And so to now come to the most recent excitement in astrophysics, the James Webb Telescope. The James Webb Telescope, as you know, perhaps is a telescope operating at infrared frequencies and launched very, very far away into Lagrange 2 of the Sun-Earth system. So it is outside of the orbit here, much further than even the moon. And as a result, the instrumentation gets cooled to very, very low temperatures, which is what we want for an infrared telescope. So 233 degrees below zero. And this is the a sketch of the, oops, sorry, I thought that was a sketch of the orbit, but it's not working. Anyway, this is just showing the Earth, the Sun, and where the telescope is. And this is just one of the first results from the telescope. So it imaged this group of galaxies called Stephan's Quintet. Yeah, so this is a picture at so-called near-infrared frequencies, and this is a picture at mid-infrared frequencies, so slightly lower frequencies, 10 microns and up. And it turns out, of course, and this was known before the James Webb Telescope, that of this quintet, only 4 galaxies are a physically, gravitationally bound system. This galaxy is very much in the foreground. This one is very much in the foreground. So there are 4, 1, 2, 3, and 4, which you can see more clearly here. 1, 2, 3, and 4, and they're interacting, so their stellar orbits are being torn apart, and then a lot of gas is also torn apart, compressed, more star formation occurs, all that is being seen here. This is something that I alluded to earlier, and a 2-dimensional spectrograph. So effectively, it's called an integral field unit, which means nothing, but basically it's a device from which you can take spectra of different pieces of the thing you're focusing at. So this is the piece of sky that is in the field of view. Each piece will have a spectrum. So it's what we call a data cube. 2 dimensions of that data cube are in the sky. So this, and the third dimension is the dimension of frequency. So for every frequency you have a spectrum, or said another way, at every for every piece of the galaxy you have a spectrum, and for every frequency you have an image. So for example, you could extract an image in some excitation line like H alpha and see what the galaxy is emitting in H alpha. And that is sort of what is shown here. So here is a slicing of this galaxy in the atomic hydrogen line. This is in an ion excited line. This is again atomic hydrogen at a different frequency, and this is molecular hydrogen. So it turns out, of course, as you would know, that molecular hydrogen excitation frequencies occur in the infrared. So now the other cool thing about doing spectroscopy is that because we know the frequencies of all these lines in the laboratory, we can measure Doppler shifts. So therefore, we can measure speeds of the whole galaxy, or the pieces of gas within the galaxy, or stars within the galaxy towards or away from us. And so, and for a data cube like this, you can get that at for the whole piece of the galaxy. Oh, sorry, this is not the velocity map. This is still the, yeah, so this is the velocity map. So here, so by the way, these are all false color pictures. I suppose, okay, all of you know what false color pictures are. The colors are not real colors because, as I said, these are all infrared frequencies, so we can't see the infrared. So the colors only represent the data. It could be intensity, it could be different frequencies, or it could, in this case, be velocity. So here, the false colors represent velocity, and blue is towards, and yellow is like minus, plus 200, and blue is minus 200. So here the false colors are representing velocity, and it is telling us that at this position there is gas moving towards us, and so forth. And this is showing the other thing that I said, the composition. So again, spectra in different positions. So this region has a spectrum like this, and it is showing molecular hydrogen. It is showing the presence of silicates, which means dust grains. And again, these frequencies are molecular hydrogen, and these are all in the so-called mid-infrared, that is over 10 microns. And this circular region has this sort of a spectrum. So it is showing evidence for iron, argon, neon, sulfur, and so forth. And this is another image that the James Webb Telescope released first out. In fact, this was the first image that President Joe Biden unraveled. And this was a very nondescript piece of sky of which a very deep image was taken. So this is, in a sense, a repeat performance from what the Hubble Space Telescope did. I don't know how many of you remember, but the Hubble Space Telescope did the same thing in 1995 for a piece of sky that was a third of the size of the moon, and saw 3,000 galaxies in that little piece, which means that, you know, you multiply that by the whole sky, and you kind of try and think about how many galaxies there are in the universe. There's a host of information here. These are foreground stars in our own Milky Way, and the spikes are instrumental artifacts. And the different colors, in this case, this is a false color picture. So the different colors indicate intensities at different frequencies. And so, and also the shapes, of course, are real. One very interesting thing here is that this where you see a very bright sort of splotch and some dim light around it. It's actually a so-called cluster of galaxies, which means many thousands of galaxies gravitationally bound, interacting and influencing each other and so forth. And this is in the foreground. So light left this cluster about 5 billion years ago, which is roughly when our solar system was formed. And it constitutes an enormous mass. And so the light around it is gravitationally bent by this mass. And you can see that these galaxies here are having this very stretched appearance. And you can also see that all of them are sort of stretched around this central emission. In fact, yeah, I think I'll stop here. No, just this one last slide. So every dot and smudge on this picture is a galaxy virtually, except for these ones with the spikes, which are stars in our own Milky Way. And some of these very, very faint things, they come from galaxies which are very, very far away. The James Webb got spectra for them, which is what is shown here. So this little bit, this galaxy inside this square is this thing here zoomed in, and this is its spectrum, and so on. Here, similar here. And from the spectrum, we can tell how much the emission lines have shifted. In other words, the redshift. And for these very, very far away things, the shifting is primarily, it's not Doppler shift, it's primarily due to the stretching of space-time due to the expansion of the universe. So we know how far they are. And so this particular object, for example, the light left this particular little smudge inside that box more than 13 billion years ago. And so that is just giving you a peek into what the James Webb Telescope is capable of. I'll stop there.
So very fascinating. Any questions? One or two questions you can have? So I think they're still enjoying those. I just have one question. So do we know about the distribution of black hole masses? Like, are most black holes massive or sort of moderate size, or is there any understanding?
That's a very good question. So there are these two kinds. Remember, I said there was this so-called stellar mass black holes, which are we think the result of the end of stellar lives. And those, as LIGO has shown, LIGO has measured up to about 175 or so. Much, much more massive than that are supposed to not happen, because these what the hell? Oh, I see. That's Ram. Okay. Because just the way how gas clouds fragment and collapse and so on. And then there are these giant black holes which cannot be the result of stellar death. So they have to have a different formation process. And the interesting thing is we know about black holes up to about 200 solar masses, and we know those which are about 10 to the 5, which is what? Which is, yeah, and up. But in between, there's a gap. And that's very annoying. We don't know why that is. And that's, yeah.
Okay, that's interesting. Yeah.
Ma'am,
Yes.
we know that the universe is expanding. Here.
Okay, so yeah.
So the distance between any two objects in the universe is also increasing. So then why any object will end up in black hole? Because the distance between the nearest black hole and this cosmic object will increase with time. So how it will end up in black hole?
So we don't expect everything to end up in a black hole, but the universe is expanding is about space-time stretching. So it's not within a bound object. So the space-time between you and me is not stretching, right? Otherwise, you would never be able to measure it. Everything would stretch, like all our meter sticks would stretch. So it's space-time which is stretching. So space-time between bound objects is stretching. But Your question is sort of, there were two things to it. There was also this thing about stuff falling into the black hole. So if stuff has to fall into the black hole, it has to come really close to the black hole. So our Milky Way, I mean, some people ask me this question that, oh, tomorrow will we land up inside the Milky Way? It's not a vacuum cleaner which will go around, you know.
But how close is close?
Very, very close. So if the sun were to turn into a black hole tomorrow, nothing would happen to us gravitationally. We would still stay there because it's gmm by r squared, which r is still the same, m is still the same. So the sun would need to compress to a diameter of about 6 kilometers in order to become a black hole. And tomorrow, if it were to turn into a black hole, of course, we would not receive light anymore and all that, but gravitationally, it wouldn't change anything. But if you go close, then of course, you know, now you can approach the sun, theoretically, up to its surface, right? And then if you go in further, the gravitational force due to the sun will go down, will start to go down. Whereas if it were a black hole, it'll go on increasing until you reach its event horizon.
Okay, so Prajval will be here after the tea time. Perhaps you know catch her. I mean, the attraction, the gravitational attraction, and then we'll ask your questions. So we'll move to the next talk. Okay. So our next speaker is Professor Ramakrishna Ramaswamy. Ram is presently visiting professor at the Department of Chemistry at IIT Delhi. And before this, he was a faculty at Jawaharlal Nehru University in Delhi. And he has also served as Vice Chancellor of the University of Hyderabad. He was educated at Madras University, IIT Kanpur and Princeton. And he has lots of interests ranging from chemical dynamics, statistical physics, and more recently, computational biology and genomics. He is elected fellow of TWAS, INSA, and the Indian Academy of Sciences. And he has also served as president of Indian Academy of Sciences. And today he'll tell us about the importance of being synchronous.
Thank you, Kavita. Thank you also to the GATI team, and it's a pleasure to be at JNC. And, you know, in this triple header program, you know, it's nice to go second, Prajval, but a very difficult act to follow. It's not clear whether, you know, the charm of black holes will overtake or not. Nevertheless, let me try to tell you a little about the idea of synchronization, which is a very, you know, after going to the edges of the universe, it feels like a very mundane thing to talk about. But, you know, such is life. So here's a picture of some insects in Malaysia. These are fireflies. And what you see over here is 1 million of them. Thanks to Prajval, I'm now talking in millions and billions and so on. But you know, there really can be 100,000 or more of these insects, and they start out by firing occasionally, but pretty soon you'll see that all of them fire in unison. Now, this is species specific, so you don't see it very much in India. These are large fireflies in Malaysia, and they're also a tourist attraction. So next time you're in Kuala Lumpur, please go and have a look at them because they're really spectacular. Each individual insect is firing. It adjusts itself to others, and then pretty soon the entire lot are firing together. This is one example of a kind of synchronous motion, and here is another. These are from YouTube, but pictures of shoals of fish, and you can see that there are large numbers of fish that are moving together. They have a joint motion. You can see that sometimes there can be 100,000 more million sardines that move in clearly some kind of pattern. A picture which I'm sure you've seen many of, murmurations of starlings. Again, you have thousands of birds, and they're all flying together, and the point, I mean, I will make the actual point later on that this is a kind of synchronization, but what you can see is a lot of correlated and concerted motion. Now, synchrony, as it, the idea of synchrony, it's among the most common forms of collective behavior that we see in nature. One common one, which we are all part of a synchronization experiment, we are all synchronized to the sun. So except for graduate students and the tortured ones among them, most of us get up around between 6 and 7 in the morning, and we go to sleep. I mean, if YouTube, there's nothing nice on Netflix, we're out to sleep by about 8, 9 o'clock, sometime like that. But the vast number of organisms on Earth are tuned to the sun because we get our energy from the sun. And this is what's called the circadian clock. Now, the sun itself, by its externality, affects all of us in a particular way. And our wake-sleep patterns, not our individual motion, but our wake-sleep patterns are synchronized to the sun, as are many, many other processes, an amazing range of them. The first person to actually talk about synchronization was not Aristotle. Remarkably, this seems to have escaped him. But Christian Huygens was the first to talk about synchronization in sort of an experiment which he just saw. There were 2 pendulum clocks in his room, and they were wound up at different times. And what he noticed was that regardless of how they were started off, pretty soon they started oscillating together, either in unison as moving together is in phase, or they're moving out of phase from one another. And if you plot the amplitude as a function of time, you'd find that both of these are coincident, or both of these are just opposite to each other. He remarked that these were in sympathy, that these 2 pendulums moved in sympathy, and he deduced that this sympathy came from the common coupling, that they were on the same platform, so they joined. So the idea is that 2 dynamical systems, 2 things that are moving, if somehow they have a connection, if somehow they have a way of communicating with each other, they turn around to synchronize. So you can do this experiment now with metronomes. There's supposed to be sound. All right. Okay, so you can see these metronomes that were started off, and they are on the same platform. Shall I start it again? Oops. Would I unmute?
No.
Let it go. Let's just watch it visually. Imagine something ticking and talking. Right. So you've got these metronomes that are oscillating. You'll see them. They started off randomly, and they're on a common platform. And pretty soon you will see that they all. It always works, and there they are now moving together in complete synchronization, even though they started off separately. All right, it's a little more spectacular with sound. Please go to YouTube, whatever metronomes, you'll find examples of, they're beautiful right now. They're all just sort of completely in sync, but you can see hundreds of them, thousands of them together. Now, there are many examples of synchronization that are known in sort of natural systems. We all just applauded for Prajval's talk, and I hope you will do so for mine too, but that will also be in a certain kind of synchronization. The circadian rhythms I've already talked about, etc. So there are a lot of different ways in which one looks at synchrony. Now, there is almost no branch of the natural sciences and sometimes even the social sciences that does not see some or the other form of synchronization. Clapping together is social behavior. Mexican waves that people perform in stadiums, etc. Those are synchronized behavior and so on. So how does one try to describe this? There's a very nice model, and I know that there are faculty in this institute that study these. If you take anything that oscillates can be described essentially as something that is going around in a circle. So if it keeps going around in a circle, in some representation, it can be thought of as an oscillator. And this kind of representation of an oscillator, it just removes all the amplitude variations and just thinks of it as moving around a circle with a very simple equation. That is, the rate of moving around the angle theta dot is equal to some frequency omega. And when you solve that out, you get a very straightforward linear equation. When you study large numbers of these, and if I'm hurrying a little, it's mostly because I'm conscious of the fact that there's not a lot of time. There's a very famous model known as the Kuramoto model that was developed, where people looked at a whole bunch of these oscillators. And this is even useful for fireflies, because between pulses, between flashes of a firefly, you can just think of it as going around some circle and then flashing whenever it comes to zero or something like that. Okay, so here you have the phase of the ith oscillator. It evolves with some frequency, and it's coupled to all the other oscillators, J. So it's aware of all the others. And it's sort of, this is a standard coupling. It's not too important why this model was developed, but it was a very good model for systems like the one that I showed you. And I'll just try to explain what's happening over here. So we took a whole bunch of oscillators and coupled them weakly. Okay, the coupling constant here is of the order of 1 by the number of oscillators. Then each of them is independent of the other. When you couple them with a slightly larger coupling force, they start, some of them come together, some of them remain apart, different numbers of them move together and apart. But when the coupling is really strong, all of them essentially coalesce into the same behavior. And if I increase the coupling even more, they would all essentially come down to the same point and just move as one. So when we saw the firefly picture, right at the beginning, the coupling was very weak. There were very few of them, and there was few of them going on and off. Then, immediately thereafter, there were a few that were going in unison and a few randomly moving around. And then towards the end, all of them were flashing together, and that's the transition that Kuramoto defined. It's a second order phase transition. There is, if people who like phase transitions can define something called an order parameter, which is 0 when you're completely disordered, and 1 when you are completely ordered, and you have a very beautiful analysis of this model. Now, if simple phase oscillators like fireflies or something going around in a circle, if this can synchronize, we see synchrony in so many other regimes, so we'd like to understand, does the coupling have to be weak? Can it be strong? Simple phase oscillators are linear. What happens if the system is nonlinear? And if it's not periodic, supposing it's chaotic motion, what happens? Can you synchronize that also? The answer to all of these is yes. And that's taken the better part of the last 30 or so years. People have been studying this kind of idea of synchronization. So one of the most famous examples of nonlinear chaotic systems is the Lorenz oscillator, this Lorenz butterfly. So it's given by 3 equations like so. And the motion on this butterfly is sensitive to initial conditions. Namely, if you start very close, but not exactly at the same point, after a little while, the trajectories will be very, very different from one another. And these are called strange attractors and so on. This is not very important. But this is what a typical motion looks like. It's not periodic. It's not something very simple. It basically oscillates up and down. It oscillates down for a little while, goes up. And I mean, this is what chaos looks like. Now, if you take two chaotic systems and you couple them, and if it was 1983 or 1990, this was the discovery that really sparked off the field, that if you took two of these Lorenz systems and you couple them in a particular way, which is called master-slave coupling, then a really remarkable thing was noticed, namely that if you couple them at a certain point in time, and the two systems were had the motions, one shown in purple and one shown in green. When they were not coupled, they were just completely independent and going wherever each liked. But the moment you switched on the coupling at a certain time, very quickly the two of them completely coalesced, even though the motion was chaotic. So the motion could be completely aperiodic and random, but because of the coupling, both the systems behaved in the same way. Now, there's been a lot of work in this area, but let me just show you that this kind of behavior is not uncommon. What these other people, Pikovsky et al., showed was that if you took this system and you coupled them, then you had three different kinds of behavior. One where you see one system has got the solid line as the orbit and the other has the dotted line. And if they were uncoupled or weakly coupled, it was just a mess. It could be any old thing. When they were strongly coupled and completely synchronized, these were identical to one another. And there was another regime that they discovered where you had this kind of behavior. Now, if you plot one variable versus the other, if it's completely uncorrelated, you just get a mess of points on the plane. If both of these are identical and you plot one versus the other, it's pretty clear you're going to get that diagonal line because x is equal to y. I'm going to have another slide on that momentarily. Somewhere over here, you find some other kind of behavior, not there and not there, but somewhere in between. This is called phase synchronization, all right? So this is the promised slide on what is. So if you have two systems, call one x and call one y, and if they are uncorrelated, then a plot of x versus y is a random scatter. Obviously, because they're not correlated at all, they're just appearing everywhere. But if x were exactly equal to y in the sense of synchronization, then you get stuff on this straight line. For the mathematically inclined, what you can immediately notice is that when you're synchronous, you are on a lower dimensional. You see, this is a two-dimensional space, and if I plotted 1,000,000 points or 1,000,000 galaxies, you'd find them all over the place completely at random. Now, if they are identical, they are on a line, which is a lower dimensional subspace of this space. So it's called the synchronization manifold, all right? So once people realized that what synchronization did was to lead you to a synchronization manifold, it was also realized that this is not a unique problem. You can synchronize things in many different ways. Even to get things to be identically synchronized, say to be on this straight line, it turns out that you can get them synchronized either by making mutual coupling or by making one master and one the slave and so on and so forth. Okay, so eventually one realized that what really happens when things synchronize is that if you've got one system, let's call it X, and you've got another system Y, somehow if you couple them and you find that eventually Y is a unique function of X, then this gave rise to the idea of generalized synchronization. And the point is that really the resulting dynamics occurs on a lower dimensional subspace, and this will be relevant to what I would like to generalize this to. About 5 minutes? 10? Okay. So there's a whole mess of mathematics, but generally speaking, any coupling that brings the dynamics to a lower dimensional subspace, I would argue, is some kind of synchrony. It may not be, the lower dimensional subspace need not be the straight line. You see, this is one where it is identical and it's a straight line. But this is also a lower dimensional subspace, and there is a kind of synchrony that's happening over here. In this particular case, it's called phase synchrony, but any old thing. So what I've been working on over the last few years is to generalize this notion of synchronization and also to try to engineer the kind of synchronization that I want, namely by demanding that the motion come to a particular submanifold. It need not be the obvious one that is x is equal to y, but I'd like any old submanifold, and the way in which I do it is described in a bunch of papers and stuff over there. It's not too important. There is a strategy. So you have the space that you want, you take a submanifold, and you can bring your dynamics onto that. Just to show you roughly how it works, if you've got one Lorenz system, I've rewritten it in x1, x2, x3, and you've got another Lorenz system there. Exact synchronization will be that x1 is equal to y1, x2 is equal to y2, and x3 is equal to y3. Okay, so that would make it just, that these variables were identical, a, b, c were all equal to 1. I can have any old manifold. So supposing I would like a manifold where A is 1, B is 2, and C is 3, for example, the mathematics that I'm not describing gives you that this is what the coupling should be. And once you have this coupling, you suddenly find that the two systems are not only coupled, but you find that the original system is here, and this one is multiplied by 2 in one side, 3 in the other side, and so on. Okay, so this just gives you a way. This is a new submanifold onto which I have gone. All right. So, I mean, there are, of course, other ways of. There are other submanifolds you can look at, but the point that I'm making is that this is a kind of synchronization that is worth considering. So, what I really want to now talk about is that you see, synchronization so far we've talked about in time. Stuff that is going up and down at the same time or oscillating in time together is what we normally call synchronization. What about doing it in space? See, the idea was that over here, one demanded that x1 is equal to a times y1, x2 is b times y2, and x3 is c times y3. I could easily well ask for x1 is equal to y1 plus a, x2 is equal to y2 plus b, and x3 is equal to y3 plus c, so that instead of having them multiplied by factors of 1, 2, and 3, I can have them separated by some factors. Well, so the constraint, because I think of synchrony as a constraint, it's on spatial separation, all right? And this happens in bird flocks, for example. So there's a photographer in Barcelona called Xavi Bu, and he's got a wonderful series of pictures called ornithographics or some such thing like that. No, ornithography. It's a series of photographs of birds. So this is a million birds together. And an individual bird, this is a time-lapsed photograph of this bird. And you can see that the wings are oscillating. And here's it's a slight, okay, so here's all reproduced with permission. But here is a set of birds that are just at the edge of the flock flying out. And you can see over here that they keep, I mean, they're not in perfect synchrony. I mean, or they're not keeping a perfect distance from one another. But there is certainly a high degree of correlation. It's not as if these are completely random. If they were completely random, they'd all be hitting each other and falling to the ground. So, so there is a high degree of correlation among these. Okay, so what we did was to extend the methods that I've just alluded to and shown you some results from, but okay, so what you're going to see momentarily is a bunch of birds, but they're going to follow an arbitrary trajectory. That is, they're going to follow this, either the blue or the green trajectory, just, something that is moving around in space. And quite honestly, all I did was to go to GNU plot and plot some particular curve. And I said, well, why don't we take a bunch of birds and make them follow that? And what you can see is, I don't know, this is just for demonstration, 20 birds or so moving around on an arbitrary trajectory, keeping a relative distance from one another with a little noise. All that was added in. But, I mean, I could put little, whatever, cartoon images on it, and you'd think that there's a flock of birds flying around. I'd go to work for Pixar. But anyway, so let me just show this again because I'm rather pleased with oof. Okay, so this is just some arbitrary group, and they move around. They've all been told to stay so much distance from each other, and they follow an arbitrary trajectory. So where does one apply an idea like this? If you are at IIT Delhi, it turns out that there is a startup company called BotLab, and they have drones. So in this image, what you see is the algorithms that we developed to keep spatial synchrony. That is to say, well, first let's just follow these drones. Oops. Okay, so here you have 3 drones moving completely moving together. One of them is the master, and the others take their signals from the master and keep a fixed distance to each other. You will see an interloper coming into the screen who's not following the rules momentarily there, see? It would have been fun to make this one also follow it. But okay, I think you get the point that this is a proof of concept demonstration that you can make three or in fact n drones move together following the rules of constrained synchronization that we've been developing over here. Okay, as of now we haven't gone much beyond 3 and 4, but but it's a question of doing the technology and doing the mathematics as one progresses. Okay. Okay, so that's really more or less what I wanted to just share with you all about. That synchronization is actually one of the most visible effects of coupling between systems. And it's a very general means through which things organize themselves spatiotemporally. Its importance in the natural world is, well beyond things like drones and what have you. Inside cells, I mean, it affects everything, ranging from the cellular, subcellular scale, all the way up till macroscopic phenomena that we are, the weather, etc., that we are able to perceive. There are many different forms of synchrony, perfect synchronization, phase synchronization, etc. But this unifying framework is to think of it as happening on a lower dimensional synchronization manifold. And as I showed you, you can play around and you can do a lot of different kinds of coupling strategies, make stuff make stuff synchronize in this particular way. And it reduces, so you think of synchrony as a constraint, it reduces the dimensionality of collective motion, and it's really widespread. Linear as well as nonlinear systems can synchronize, weak and strong coupling can synchronize, chaotic and regular dynamics can synchronize. What I haven't shown you is how in the presence of noise you can synchronize. And so it becomes very relevant in basic areas as well as applied areas. And with that, let me thank you for your attention. Synchronous.
Thanks, Ram.
Yeah.
Yeah.
So I study circadian rhythm, so obviously my question is kind of colored by that. I was wondering whether it's true also in other systems that are not necessarily those in cells or in biological systems, that you don't find too many examples that are on the straight line and too many examples on the extreme end, but it seems more like those that are approaching the manifold that is close to the straight line. And do you think that there are reasons for that?
Yeah. Okay. I mean, actually, it's one of those questions where it's not easy to give a straight answer that it is this way. Our approach to how to synchronize onto the manifold is to apply a constraint that brings you onto this line, and then to make you stay on that line. It turns out that the line need not be stable. So what happens is that you come onto that synchronization manifold and then you escape. Then you come back onto that manifold and then you escape. So this is a very common phenomenon that one sees, that when the manifold itself is not a stable manifold, it's not attracting in all directions, then you can approach it and escape and approach it and escape and so on. So because in your system, the coupling is determined by whatever it is. I have a lot more control because I'm working with engineering systems. So that's one difference between these two kinds of situations. See, engineered systems are much more stable, right? They're not as chaotic as, autonomous systems that are left to themselves, where if you are intermittent, yes, you do have problems when you come very close to that, the tangency points and so on. But engineered systems are actually much more stable. Right? The problem that I face with engineered systems is that if I have one master and a whole bunch of slaves, and somebody shoots the master down, what? Right. So one has to sort of try to put in mechanisms to make sure that somebody else takes over and so on and so forth. So those are more the issues in engineered systems. Natural systems is of course different.
I'm sure there are lots of more questions, but we are running a little behind schedule. So we'll have Ram once again. Okay.
You do see these fireflies synchronized in Nagar.
Take a video and put it on YouTube, Prajval, please. No, because the only YouTubes that are available are from Selangor in Malaysia, actually. And I looked for them from Chhattisgarh, but there was nothing. There was some report of it, but this business of whole trees going ablaze. If they are there in Nagarhole, please put them up. Thank you.
Okay. So we'll move to the second part of the symposium, and we'll start with Ram, who will talk about representational bias in Indian academia. 15 minutes.
15 minutes. To talk about bias in Indian academia, you need 15 days. Okay, this is, removing the synchrony hat and putting on the gender hat. And yeah, all right. Okay, 15 minutes means that this is not going well?
Share the screen.
Okay, please. Okay, so while you all are looking at that photograph, that was a 1926 photograph of the Solvay conference, where you can see that Marie Curie is the, shall I start my slide? Sure. Yeah. Okay, so this was from 1926, and you can see in this lineup of luminaries, there is only one woman, and in 2013, Eileen Pollack said, why are there still so few women in science? Okay, it is a truth that we should take more or less, we should admit that much of Indian science is today dominated by a Savarna male elite. Upper caste men dominate Indian science, and there is nobody who there's no blameless party anywhere over here. So I'm not speaking from some other position. I am as much a part of the problem as anybody else. In our country, we know that social diversity is legislated at all levels. We've got it all written down in the Constitution and so on. We have reservation policies, but when it finally comes down and you look at numbers, including among us, you'll find that the numbers are very different from what one would have wanted. Barriers are not easy to overcome. And so, as Raja already alluded to in his introductory words over here, as you go up any particular sequence, any particular ladder, the representation of any group actually gets more skewed along this so-called pipeline. And the diversity that we would like to see in our body, academic bodies, this reduces along the hierarchy when it comes especially to recognition and positions of leadership. Now, when it comes to a business of gender, frequently one is, so they point to examples like Indira Gandhi or Draupadi Murmu and say that, look, you've got very powerful positions occupied by women, but the fact of the matter is that there is a huge intersection of politics and class and caste that goes into all these decisions that catapult people into certain positions. In the sciences, in academics, there are about 5 women directors of major laboratories, and there are few women vice chancellors. Okay. But outside academics, there are a few women scientific entrepreneurs, and at least in Bangalore, for example, Kiran Mazumdar, and so on. But this is a very skewed and inaccurate representation of the real position. In academic science, especially at the higher levels of prestige and power and whatever decision making, there are very few women. And it's not just a problem of India, this is also a problem in many countries across the world. And it's something that one needs to understand. Okay, so this lack of persistence has been called the leaky pipeline. Now, in about 15 years ago, Rohini Godbole and I edited a book which some of you might have seen. It's called Leelavati's Daughters, the Women Scientists of India. And our question at that time was, what does it take to be a woman scientist in India at that time? What was the basic feeling of Indian women in science? And rather than look towards history, world history, or Marie Curies of this world, we thought we would ask a representation of Indian women scientists. And this book was received reasonably well. It was reviewed in Nature, leading to my only publication in Nature. Excuse me, it's not a publication per se, but if you notice very carefully, the photograph is mine. All right, so that is an even higher level of achievement. I am a nature photographer. All right. Okay, but more seriously, Leelavati's daughters gave a start to the community to talk about it, because we were talking about ordinary women who were just doing science, and we asked the question of how they were going. And there are, actually, I'm pleased to see there are at least 3, if not more, Leelavati's daughters in the audience today. The actual representation of women is worse than what any of these numbers say, because people count numbers as they like them and whichever way they want to make things look good. Take any of the scientific academies, no more than 10% of the academy fellowship is female. Less than 5% of all Bhatnagar awardees are female. And as I already said, fewer than 10 directors of major laboratories. And if you look at the granularity of the data, the participation is very uneven. If you look across regions, there are huge parts of our country where women do not figure in science. And there are many communities where the number of women in science is very low. And the exceptions just confirm. There are many women who are highlighted in this book. There are almost 100, but I want to just point out to a few. Janaki Yamal was a path breaker, but she was the founding fellow of the Indian Academy of Sciences. She was given a Padma Shri. She did a lot of work in botany and cytobiology. And by choice or by design, she was single, and that had a certain set of consequences. Another person who I'd like to identify over here, I don't know if Hila is around, but Darshan Ranganathan was at IIT Kanpur, where her husband was on the faculty. And as a consequence of hiring practices, she was never given a job so long as he was at the institute. When he retired, she moved first to Trivandrum and then to IICT in Hyderabad. And in 10 years or less, she outshone, in volume and in quality, she outshone the work that he had done. So her independent career was very short, but it was spectacular. And unfortunately, she died at the age of 60. Kamala Soni, of course, for Bangalore is an important figure to remember, because she was not allowed to do a PhD by C.V. Raman. And then she went on to Cambridge, got a PhD, and became the first director of the Institute of Science in Mumbai. Right. Now, in Leelavati's daughters, one of the common themes that all these essays, after a while, they all begin to sound the same. Why? Because everyone says how important parental support was. They all point to a strong, father encouraged me to do science. And then if they are, post-marriage, they always talk about the support they got from either the mother-in-law or, some kind of familial support that was available. I'm more concerned about the fact that most of them talked about the importance of role models. They all had people to look up to, and people whom they could identify with, that they could look up to, and mentors and senior colleagues who could help. And when you look at the data, the actual data, and I've just chosen to show you what, this is available for a whole lot of institutions, but I've just shown you what's available for IITs, for the IITs. The total number of faculty members in IIT Delhi, which is in yellow, is almost 500. And there are 60 women, all right? So that's 12%. And if you think 12% is really bad, if you look at something which is equally large, like IIT Bombay, 600, you've got 73 women or 11%. The really good statistics is from IIT Palkad, but they only have 86 faculty members and 17 women. And the worst is IIT Jammu, where you've got 76 faculty members and no women. Now, because of the admission policies, you'll find that women are admitted in very large numbers to institutions, to the IITs. So in the student body, you've got, as you see over here, you've got 20% or more who are women on as a composition of the student body. Where do they find mentors? Where do they find role models? So it is a real problem, and this is a problem of the IITs. When you look at the data at a more granular level, the red are the number of women, and the black numbers are the total number. So at IIT Delhi, in chemistry, my own department, so to speak, out of 34 faculty members, there's one woman. Okay. Engineering is actually much worse, because in 264 faculty in all the engineering put together, there's only 26. And there are big departments like electrical engineering where there are no women. And 50% of the students are girls or women. All right. So this is a problem. Computer science, again, very large number of women choose to do computer science, 2 out of 35. Maths is 8 out of 20. Well, the numbers are up there. Okay. So this is uniformly low, especially compared to the student composition, and this can be very detrimental to institutional mentoring. All right. Some years ago, we did a survey, an actual sociological survey. Anita Kurup of the National Institute of Advanced Studies did this for us. And the data tells us, I mean, it just confirms everything. But it says that, or it can be seen that one of the most significant barriers for women in science is maintaining a career inside an organization that is designed by and for men. And in this leaky pipeline survey, going to just, I mean, much of this is stuff that one knows, but let me tell you that the survey actually looked at about 2,000 women with a PhD in science, and it covered, it covered 568 working women scientists and 161 men working scientists. And the other numbers, the subtraction numbers are people who have left science or are not working. All right. So the categories are those who just went into undergraduate teaching, managerial or temporary research posts, and many who are not working because they were either devoting time to their family or what have you. Some of the things that we discovered through this kind of study was that the selection process in our institutions is not at all transparent. Why somebody got shortlisted, excuse me, I have to catch a flight. I know this is how you put men down. All right. Okay. It's also necessary to have gender audits, and that is why some initiative like the GATI program is good, but it's also important not to stop there. Because 85% of the women who work say they can manage to have a family and to manage their work if you just let them be. A larger number of women choose not to get married or are not do not find it possible or necessary to be married. And what this shows, and this is compared to 3% of men who are out of this survey, so fewer men than women find it difficult to balance a career and a family. We need to worry about it because in today's India, many academics marry other academics. just as many doctors marry other doctors, or many whatever of any particular species marry, of the same species. So, I mean, one advice is that please look outside the lab and not inside the lab, because this is going to be a real problem for you later on. But no, jokes aside, many institutions really discourage linked appointments. Smaller institutions and more autonomous ones can afford to bend the rules, but it gets very difficult inside state or central universities or governmental organizations. More importantly, I think we need a commitment to gender, we need to be sensitive to gender issues, not just facilitating women. And I would urge all of you to read the GATI baseline document and see exactly how patronizing and patriarchal it is in its own way. Right. Now, the important thing, and Kavita, I'm going to request for at least 2 more minutes. Majority of women who did not have jobs, okay, they actually said that they were not given jobs. Not that they we did not get jobs, and very few said that they didn't choose to have a career because of family reasons. And there is, therefore, some kind of a bias at the institutional level. And I just want to put out for an audience of, graduate students and faculty that there is an idea that was put forward by the philosopher Miranda Fricker, who talks about epistemic injustice. Okay, this is a kind of injustice which is very particular because it's a wrong being done to people in their capacity as a knower, as somebody who knows something. Epistemic injustice, it's due to a prejudice. One type of it is due to a prejudice causing a hearer to assign a lower level of credibility to a speaker because of their identity or who they are. Due to bias against people of a particular race or gender, whatever they say, their testimony is called into question. And this is something that we, when you go abroad, you face it as you're an Indian, what do you know? Over here, it comes to a case of, you're a woman, what do you know? It often comes down to a case of that. And there is another kind, it's a little more subtle. When you have no idea of the life experience of somebody, how can you even know what they are saying and whether it is true or not? And that is because our social milieu tends to be so non-diverse that we don't have an idea of an experience different from the majority experience. And this makes us evaluate people at interviews, at various kinds of evaluatory forums. We give them lower marks because we don't even know what they are talking about, right? Anyway, so this highlights the need for diversity in bodies such as this. I mean, I do realize that the institution is small, but still, it is important to have diversity. And we can't make things more diverse unless we really try. It's important because the more diverse we are, we're just going to do better work. We're going to do better work because we're going to have different points of view, different critiques, different ways of interacting with each other, and different experiences that we bring to the table. Let me just conclude with a modest proposal. At this time, many institutions are undertaking special drives and special this and special that, and different selection procedures for different categories can be problematic. We are, beg your pardon? No. It's a satirical piece by Jonathan Swift. Well, so it is a modest proposal, all right? Yeah. Wikipedia it. This is, okay, so the point that I want to make is the following, and it is for administrators, colleagues, faculty, etc. If you have, we are one body. And it is better to have everybody evaluated together in the same race rather than having different races for different groups of people. One model that has worked in whatever complicated way is the JNU model of deprivation points, where people who were deprived who felt some measure of deprivation, either by gender issues or by social groups or by living in economically depressed areas or for any other reason, a physical handicap, whatever, all these points were deprivation could be counted, and this was included in their evaluation process so that a person could cross a threshold by recognizing deprivation. Now, I know that there are students from JNU here who are both in the student body as well as there have been postdocs from JNU and faculty members over here. And this is a model that, in a sense, it works because it recognizes that the body that you want to create is a diverse body. Gender is an important component, and therefore it is good to take a measure of it. But there are other types of diversity that we need to have in the body, and other types of deprivation that we need to count. So if we are sensitive to the fact that we need a faculty diversity so that the students, in a sense, will have a wider range of people to interact with, to learn from, and to admire and aspire to be like, then it can be a more representative and I believe a more productive and a more successful academic body, right? There are more things that I have to say, but finally, for a woman to continue to have a career and a competitive one, it's really like this picture of an acrobat from 2 centuries ago. You're on a tightrope, you're juggling a whole bunch of knives, and one slip one way or the other can be a little, there can be a lot to pay for slips in this business. So with that, let me stop. Thank you.
Yeah. So I had talked about the discovery of a 4 million solar mass black hole in the center of our Milky Way, and how that discovery won the Nobel Prize in 2020. And one of the winners was Andrea Ghez. And in fact, this simulation that I showed was data from her experiment. And so one of the things she has said in her many interviews is, she says, I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you can get into MIT, you can get into Caltech, etc. Now, if I had heard these words half a century ago when I was growing up, I would have been very surprised. Because I was born the year after Sputnik was launched. Yuri Gagarin and Valentina Tereshkova were my childhood heroes. My parents bought me, when I was about 8 years old, they bought me this book called The Atom, which had these beautiful color illustrations. And one of Rutherford's experiment, I was completely floored by that experiment. This is, of course, a picture pulled from the internet. I don't have that book anymore, but I think all of you know what I'm talking about. They bought me these books by Sawyer on mathematics, which are, I think, the best books on mathematics ever, which give you a real intuitive feel for it and never a sense of fear. I, of course, read Marie Curie's biography. I also read a lot of Soviet science fiction. So for me, it wasn't really something amazing at all to develop an interest in science and then go into science and so on. And I always thought of the educational space as something that was welcoming of everybody. I went to a girls' school. The only men teachers were for dance and music and Kannada. All my other teachers were women, including science, NCC, physical games and everything. I went to a girls' college where it was more mixed, but nevertheless, the only PhD in my college was a woman with a PhD in physics. I had a maths professor and a physics professor who were Roman Catholic nuns and so on. So I never thought of the educational space as gendered. Of course, gender inequity was all around us. It was in our face. But somehow I thought of the science space, the educational space is different. And it was only when I went to IIT for a master's that gender inequity within the sciences hit me. So it is this thing. I mean, Ram mentioned increasing gap in numbers as you go up the hierarchy. But an even more important thing, I think, is that increase in the gap as you go up in so-called eliteness, so-called institutions of excellence. So if another sort of thing of eliteness is the Nobel Prize, and of course, all of you know that there are only 4, taking physics as an example, which is one of the worst gender gaps in the academic disciplines. There are only 4 of physics Nobel Prizes that have gone to women, more than a half a century of gap between them. And what is worse is that there have been so many of these transformational discoveries, whether of Cecilia Payne-Gaposchkin, who found that our sun was mostly made of hydrogen, Bibha Chowdhury from India, Vera Rubin and Jocelyn Bell. All of these made transformational discoveries, and there are many more. And they did not get the Nobel Prize for the only reason that they were women. So the fact that there's a gender gap is incontrovertible all across the world. If you look at statistics, men are overrepresented at all levels as well. So what do we do about it? Do we ask girls to be strong? Do we ask women to take karate classes to build confidence? Do we advise postponing childbearing for the right moment? Or do we suggest, be mindful of your clothing when you go for conferences? Do we say, have skill building workshops for women? Do we organize special science camps for girls? Do we build more toilets for women? Do we increase maternity leave? Do we have quotas for women? So I would like to examine the trope for data from India that there is a lack of interest in science among girls, because that's supposed to be the motivation to have science camps only for girls, right? So if you look at the National Inspire Fellowships, oh, sorry, my animations have gone messed up. If you look at the National Inspire Fellowships for all sciences, this is as of 2015 itself, more than 50% are won by girls, and 50% are won in physics by girls. The Indian Academy of Sciences Fellowships, these are data thanks to help by Ram, who was president at the time, and this shows both the pool of applicants and the selected, and more than 50% women win them, and enrollment in undergraduate science is also 40%. So none of these indicate that there is a lack of interest in science among girls. But despite this evidence, the trope that the girls are not attracted to science is really widespread in India. And special interventions to attract girls feel really good and warm and fuzzy, but it is clearly barking up the wrong tree. And unfortunately, the GATI scheme also reflects this sort of notion. These are images from the GATI advertising video, and it says stuff like science camps के माध्यम से अभिरुचि और दक्षता बढ़ाएगी और छात्रों में पैदा होगा आत्मविश्वास. As if to say that there is absolutely no evidence that there is a lack of Atmavishwas, or there is a lack of Abhiruchi or Dakshata, for that matter. It's worse than that. This survey of 4 high schools in Dehradun, published in Current Science a couple of years ago, not only shows that a minimum of 30% girls said that they were interested in one of the science subjects, but they also tested perceptions. So the perception that fewer girls than boys are interested in higher studies in science and maths, and more boys than girls said yes, more girls than boys said no, and more boys than girls said don't know. They also tested this perception: science and maths is difficult and girls go for easier subjects. Again, more boys than girls said yes. So it is the boys who are socialized to think that girls are bad at science, right? So therefore, education seems to reinforce societal mindsets rather than enable questioning of them, which is the opposite of what we expect education to do. And it seems to do that more for the boys as far as this experiment is concerned. So what is the need of the hour? The need of the hour is not science camps for girls. The need of the hour is to teach all, to make sure that all young minds must learn that people of all genders can competently do science. So science camps need to dismantle social constructs. So what is a social construct? It is something that does not exist in nature, but it is created by society, and it exists because of all of our tacit agreement. And that's why it's there. For example, women bus drivers, right? 50% of bus drivers are women in the US. But in India, if there is a woman bus driver, they make headlines. There's probably a handful across the country. And this is Mamata. This is a very proud photograph of mine. Mamata, who came for my science outreach talk, and she's a bus driver from Bengaluru. So if you look at the, okay, so firstly, any attempt to address gender inequity or inequity on even other dimensions such as caste and so on, the acknowledgement that they are social constructs is the first step. And it also means, in the case of gender, that one has to acknowledge that gender is a fluid concept, shaped by many factors that include social expectations in a major way. So this is, I have just pulled off a screenshot from the GATI form, where they are not acknowledging gender as a social construct, because if you did, then you would say women and men rather than female and male. And also, this is a very binary construct. I mean, even the NEP talks about transgender and so forth. So it is unfortunate that the GATI framework did not incorporate gender as a fluid concept. Now, I want to come to discrimination within the profession. So there was a study by Neelam Kumar as early as 2001, where 4 research institutions were surveyed, and she found no productivity deficit among women. And she also found that women are systematically lower in the science hierarchy, despite there being no productivity deficit. And the mean age of women who were professors or equivalent was significantly higher than that for men. And so there is indeed discrimination within the profession, because remember, there was no productivity deficit. And we found the same thing when we did a study in 2015, where this is the fraction of PhDs in physics who are employed in higher education in India, which is roughly 20%, which is as it is low. But then, as Ram mentioned, if you go to the more prestigious things, like this is the Academy Fellowships, this is the C.V. Raman Lectures of the Indian Physics Association, which is considered very prestigious, and this is governing councils. And so that number drops from even this 20% to almost single digits. So when the gender fraction drops with respect to the pool, that means there is a systemic barrier and a systemic problem with the process. So what are the mechanisms by which these processes manifest? An astrophysicist called Meg Urey from Yale University once said, discrimination isn't a thunderbolt. It isn't an abrupt slap in the face. It's the slow drumbeat of being underappreciated, feeling uncomfortable, and encountering roadblocks around the path to success, along the path to success. And some of these cartoons sort of depict that bias that all of us experience at some time or another. I'm sure all of you have seen these cartoons before. This is from Resonance in March 2017. And one very typical manifestation of that kind of a bias is not even a very prestigious thing, but just the magazine Resonance, which we looked at. And during 2014 to 2016, this is the gender statistics of the authors in Resonance, which are invited pieces mostly. And in 2017, this is what the numbers showed. This was a special issue that we guest edited with an all-women authorship. Ram had a major role to play in that. And you can see in our editorial piece, we wrote that we hope this is the first and the last such thing, because our goal was to demonstrate that there is no shortage of women authors to write for magazines such as Resonance, or indeed any kind of science writing. I had the responsibility of assembling the authors. I had a list of 20 because I thought 50% would say no. Nobody said no. So in fact, I had this list of spare authors whom I had not contacted at all. But you can see that the editorial board never read our editorial, and they went back to business as usual after March. And the same thing held for 2018, except for a couple of issues here, which I have circled, which have a better gender ratio. This, incidentally, is by TNC Vidya. She was the guest editor that time, and so she's managed a pretty good ratio. I don't think it was very conscious. I think just naturally it came out like that. So these are some examples of the everyday. These are comments that I've actually heard in the enterprise, within the enterprise. So like, we've already have one. Why do we need another woman in the department, right? So what her qualifications or merit is doesn't matter. No point in shortlisting her. Her boyfriend lives in wherever, somewhere else. Her husband is already here. How can we give 2 jobs to the same family? Why do you want to do research? Your husband is earning twice as much. Your husband is able to give you a car. Why do you need a job as a scientist? And this is to a student, I'm like your father, etc. Or, she's like everybody's mother, etc. These kind of comments. Assigning jobs that involve care, particularly to women staff. Assuming that if a woman wears only saris, then she doesn't drink alcohol. Assuming that if a woman drinks alcohol, then she's open to sex. All these kinds of things are things which we have encountered. This is this advertisement of the mobility scheme by DST, but I think I'll skip that because I've been already signaled to. So this is, as Ram said, I mean, the GATI framework itself is very patriarchal, and that is problematic because it is not going to then help address the real problem. It is not going to help address the root cause. So for example, about GATI, it is said, the schemes will holistically address the needs of women scientists, which are related to culture, finance, building confidence, motivation. It's all in the nature of fixing the women. Even the name, gender advancement, right? I've been wondering what that's really puzzled me, because what we want is gender suppression. We want gender to become not salient in academic spaces. So what does it mean, gender advancement? I really don't understand. Anyway, because of all these systemic barriers and because the evidence is so overpowering, in 2016, on Women's Day, in fact, I managed to convince a bunch of my senior colleagues, including some people in the audience and Ram, of course, and made a proposal to the Indian Physics Association to launch a gender in physics working group. A year later, they did launch it. The point is that unless the systemic problem is acknowledged, change will be too slow. And it will come at a huge cost. Cost meaning people who will actually leave the profession. And among scientists, while they do acknowledge the gender gap, they do not acknowledge that there is gender discrimination within the profession. And the other important thing, of course, is that regardless of our gender, we are all brought up to accept sexist thought and sexist action. And so we can't assume that just because one of us is a woman, we are going to be less gender biased. We can't assume that because we are all entrenched in that culture. So this is the problem. And everybody knows that this is not the right solution. And many people advocate this. But this is still fixing the women. And it is not taking into account the evidence. So what we really need is to be mindful of the evidence and do this. Namely, we need to fix the tree. The tree is what is bent, and that is what we need to fix. By the way, the government of India recognized this problem very, very early. This is a statement by the Science and Technology Minister of the time, at the time, 2008. However, it seems that all that effort and that funding, when it gets translated into implementation within science, policies get framed in a very patriarchal way. So the Gender and Physics Working Group has asked the questions which need to be asked, namely, does any intervention, first of all, meet the need of the hour? And does it seed or does it hinder cultural change? And so we came up with this thing called the Hyderabad Charter for Gender Equity in Physics, which we kind of finalized at a first of its kind conference that we had in the University of Hyderabad in 2019. So this is the Hyderabad Charter for Gender Equity in Physics, and about 350 physicists in India have endorsed it. I, of course, won't go through everything, but it is meant to be a starting point for the institutions to debate. Not just physics institutions, it is open source, anyone can adopt it. And it has various recommendations for the classroom, for the department, for conferences, for editorial boards, for outreach exhibitions, for funding agencies, and so on. And I think I'll skip this. So some of the things which are very different from how the GATI project is framed, not all, there are many more things which are very different. For example, closing the quantitative gender gap at all levels of physics practice is a necessary step to achieve equality, but it is not a sufficient step. The practice of physics is a social activity, and addressing its gender bias requires insights from the social sciences. When a process of selection reduces the gender fraction from that in the pool, it is a signature of a biased process. So some examples of recommendations that I would put together is in hiring processes, there should be no hidden norms. For example, a person is disqualified from applying regardless of her merit if her spouse is already hired in the institution. That's a hidden norm, that's discriminatory, that's not in keeping with the claim of a meritocracy. So that's why we recommend that a diversity officer be an observer on all committees in institutions. A diversity officer has the expertise to sense non-diverse processes, to sense non-transparency, to sense lack of accountability. They may not be subject experts, so that's why they are observers. They do not vote on hiring or selection, but they are there to make sure that the processes are as unbiased as possible. Another example is when you organize mentoring and outreach programs. So have the scientist mentors undergone bias training. Otherwise, they tend to treat the women students very differently from the men students. I've seen this all the time, that, you know, the men students will be told, yeah, stick with your passion, go for it, etc. The women will be told, you have to work very hard, you know, you have to manage your family. And I've never heard a young man scientist being told, you have to work really hard because you have to manage your family and your science. I've never heard this. So this is the problem. So then the scientists who offer to mentor or who offer to do outreach, they do need to undergo bias training. Some language changes. These are small things, but I think it's really important because I've heard for too long, for too many decades, that, oh, you're making a big deal out of a small thing, but it never changes. It's not changed in half a century. Okay, so male, female to men, women reflects more the idea that gender is a social construct, because the words men and women encapsulate that social construction more than the biological words. I was very surprised that JNC lists the GATI program under outreach, because GATI is supposed to be inward looking. So I don't know what that means. I think that it's important, this thing about language. I still see these Mrs. things here. I mean, unless, if you want to treat men and women equally, you should list all the men like this, right? And if you think this is ridiculous, then please get rid of the Mrs., right? And I want to end by saying scrutiny of interventions is really important. Is it evidence-based and is it the need of the hour? Does it seed or hinder culture change? Social biases is strongly entrenched in our academic practice and science. So therefore, stop fixing the women and the girls. Equality education is the need of the hour for everybody. And equality education is particularly required for senior faculty and management, regardless of their gender. Equality and diversity work is everyone's responsibility. And numbers do not tell the whole story. So thank you.
Yeah, I thought that theoretical physics is the most challenging thing in the world. Okay, so I think we have, almost running out of time, and especially since Ram has to leave. So what I would like to do now is to just tell you that, we had ran this survey competition, and the reason we wanted that was to attract many young people here to, listen to these views and, look forward, sort of think more progressive manner, don't repeat our mistakes, right? So I'm happy to say that we received over 20 responses.
You should be wearing this, no?
It's So we received more than 20 responses from most units in JNC and almost equal number of male and female participants. And I just wanted to summarize the responses because that will tell you how young people in this in JNC are thinking. So our first question was how we can increase representation of women in science. So there were sort of common answers from most people. So one was to have female role models in school textbooks. Other thing they said was to organize gender sensitization and mentorship programs at workplace. Our second question was, what's the role of men in combating the gender bias problem in academia? So most female respondents consistently said, and what you already heard in these talks of Ram and Prajval, they all said that women's work they feel is underestimated and undervalued, and society's attitudes has to change. And they also, both male and female respondents said that they urged male colleagues to call out instances of bad behavior at work. Could be shouting, all kinds of bad behavior. You are already familiar with what I mean. Okay, and the third question was, what are the institutional policies or practices that could help? And most respondents said that we need more women in decision-making bodies and more female faculty. So I want to thank all of you for your participation and for your thoughtful responses. And this will be valuable when we apply, when we prepare our application for GATI. So there are prizes for this competition, and we had announced 4 prizes. But you did such a great job, enthusiastically participated, and wrote your thoughts. We decided to give instead of 4, 5 prizes. So I would now like to request Professor Kulkarni to give out these prizes. So I'll call out the names and please come and collect. Yeah. Mr. Rutvich Kulkarni. Thank you. Ms. Rijna Datta. Ms. Rijna is also part of our GSAT. Mr. Mohammad Jassel. Miss Gunjan Sharma, she is not here, I think. So, Naina Debraj, can you come and collect on her behalf? And Ms. Nijita Matthew. Thank you. So all of you in this hall will also receive participation certificates, which you can collect from your unit secretary or reception. And of course, the point of all this, prizes and certificates is not like it's going to solve a problem, but at least you will come here and listen and go back and think about it. Okay, and I would now like to request Mr. Srinivasan for a vote of thanks.
Thank you, Professor Kavita Jain. I would like to not to take much of the time as Professor is in the hurry today. So, at the first instance, I would like to thank our President, Professor G. Kulkarni, for his able guidance and support in successful implementation of the GATI programs at our center. And on behalf of JNCASR and the whole GATI team, I would like to express our sincere and heartfelt thanks to Professor Ramaswamy and Professor Prajval Shastri. And also I'd like to thank you, ma'am, for your kind comments on the JNC's website. We appreciate it. Thank you so much. I'm sure our director, our president will definitely look into it. Thank you, sir. Of course, we had a wonderful, inspiring lectures too from both of you. So thank you so much for this. And we would also thank our Dean, Professor Raja, for his wonderful welcome note about the GATI programs that is being done. And of course, we have to have a special thanks to Professor Kavita Jain, who has been handling so efficiently the GATI programs at our centers by coordinating with various agencies and also with our Department of Science and Technology. And thanks to our Ms. Nabonita, my colleague Nabonita Guha, Senior Library cum Information Officer, and her colleague Anjana for effectively coordinating with Professor Kavita Jain and supporting her. So thanks also due to our administrative officer as well as the whole GATI team. As a team as a whole has done a wonderful job today in organizing such a wonderful program. And of course, the last thanks are due to all the people who are directly and indirectly connected in organizing this program, like people who did audio video program, photo shoot, dining hall people, and everyone. So thanks a lot, and please do join us for the tea, which is hosted outside the hall. Thank you very, very much for all your patience and all your inputs and suggestions. Thank you so much.